Today we're going to continue our review of global wind systems and pressure belts. The last time, if you remember, we talked about this diagram and the arrows on the diagram, and we identified the arrows as representing the major wind systems of the Earth. These being the names of the major wind systems of the Earth. And over to the left, you have the critical degrees of latitude that you need to remember. And of course, inside of the diagram, you have the arrows representing the global wind systems. At this stage, you should be less concerned with the arrows on the outside of the diagram. We'll talk about those later. But keep in mind, as we look at this diagram, what we want the diagram to tell us. Any diagram is a representation of reality, and the purpose of the diagram is to help explain basic concepts. And while diagrams may seem complex sometimes, they actually can help us understand a great deal about whatever it is we're studying. It's simply a matter of becoming familiar with the diagram so that we can gain the benefit of having the diagram tell us some aspect of reality. And so the way in which you should approach studying a diagram such as this is, number one, keep in mind the basis of the diagram. And the basis of the diagram we talked about the other day with respect to pressure and wind, the second and third elements of weather and climate that we're going to study during this particular part of the course. And so we know then the basic nature of these two elements, pressure and wind. And that is a relationship where wind is affected directly by atmospheric pressure. Specifically, wind is created by the pressure gradient or the gradient force. That is the differential in pressure between two locations. On the landscape will cause air to move directly from high pressure to low pressure. The greater the differential, the greater the air movement from high pressure to low pressure. Conversely, the less the differential, the less the velocity of wind from high pressure to low pressure. So that if there is no differential at all in pressure between two locations, then essentially you will have no air movement in a horizontal direction, which we define as wind. And so understanding that basic relationship between wind and pressure, we can better understand what the arrows mean in this particular diagram. Now, as I said, the last time we talked about the arrows as representing your major wind systems. But we can use this basic nature of the wind-pressure relationship to understand the reason why the arrows are pointing in the directions that they're pointing. But in order to understand that, we also need to consider global belts of pressure in addition to the wind systems that are indicated on this diagram. And so the global pressure belts correspond with the strategic degrees of latitude that are indicated. And so at the equator, you have a general belt of low pressure. At 30 degrees north, as well as 30 degrees south, you have a general belt of high pressure. And at 60 degrees north and at 60 degrees south, you have another belt of low pressure. 90 degrees north and 90 degrees south above the North Pole and the South Pole, you have another belt of high pressure over the North Pole and the South Pole. So as we move, for example, from the North Pole to the South Pole, as we cross these strategic degrees of latitude, we essentially go from high pressure at the North Pole to low pressure at 60 degrees north, to high pressure at 30 degrees north, to low pressure at the equator, to another high pressure belt along 30 degrees south, and another low pressure belt at 60 degrees south, and then finally a high pressure area over the South Pole. So these are your global pressure belts that have a significant effect on your global wind systems. And so again, in order to understand the effect, we have to go back to the nature of the relationship between wind and pressure. That is the gradient force, or the pressure gradient. And so, according to this relationship, these global winds should move directly from, say, a high pressure belt at 30 degrees north to the low pressure belt along the equator. In other words, winds should be affected by the pressure gradient or gradient force, the force enacted on winds that make them move directly from high pressure to low pressure. But because of the Earth's rotation, global winds tend to be deflected, either to the right or to the left of flow. So that in the northern hemisphere, as the Earth rotates on its axis, winds tend to be deflected to the right of flow. So that if air has a normal tendency, being affected by the gradient force, to move directly from high pressure at 30 degrees north to low pressure at the equator, then because of the Coriolis force, which is a force caused by the Earth's rotation, which makes winds be deflected to the right in the northern hemisphere, air will tend to be deflected southwestward as air moves from 30 degrees north toward the equator. And as a result, you have being created the northeast trade winds. And conversely, in the southern hemisphere, where air would ordinarily move directly from the high pressure belt to the low pressure belt at the equator, from 30 degrees south to the equator, being affected by the gradient force of the pressure gradient, because of the Earth's rotation, and because winds are affected by the Earth's rotation, air has a tendency to be deflected to the left of flow. And so winds are deflected in this fashion. And as a result, you have being created the southeast trade winds. Now, another thing that you need to remember is the fact that these winds are named based on the direction in which they come from. So that, for example, these winds which originate at 30 degrees north latitude and flow toward the southwest and toward the equator, these winds originate in the northeast and flow toward the southwest. So therefore, they are referred to as the northeast trade winds because they originate in the northeast from this particular latitude and flow toward the equator. Similarly, in the southern hemisphere, the southeast trade winds originate in the southeast along 30 degrees south latitude and flow toward the equator as they're deflected to the left. And so as a result, they're referred to as the southeast trade winds. And so this is the way in which the trade winds are set up with respect to their names, and also we can understand the reason why these winds flow in the direction in which they flow, because of the pressure gradient force as well as the Coriolis force. Now, the Coriolis force is a force that you need to become more familiar with, and the textbook explains the Coriolis force very well. And this is the way in which you spell it, Coriolis force. Okay, so are there any questions as far as understanding the basic nature of the diagram, that is being dependent on actually two forces, the Coriolis force as well as the pressure gradient force, and also the configuration of the arrows and the lines on the diagram. Now, the last thing that we want to talk about today, and probably most importantly, we want to understand the significance of a diagram such as this. In other words, we know the basic nature of the pressure-wind relationship. We should know by this time the basic configuration of the diagram. But the final thing that we want to understand about the diagram is, what does it tell us about reality with respect to specific weather situations in specific areas. And so we can look specifically at the strategic degrees of latitude in order to understand what happens at these locations as a result of these wind systems as they are created by the global pressure belts. And so this is what the information at the bottom of the transparency tells us. That is, what is the weather situation at these strategic degrees of latitude? At the equator, at 30 degrees north and south latitude, and finally at 60 degrees north and south latitude. What is the weather situation like at these degrees of latitude? Well, at the equator, which you have information shown to the left on the transparency, you have basic characteristics associated with this particular low pressure area. Number one, you have a situation of convergence. Now, convergence simply means coming together. And so at the equator, what you have is two wind systems coming together. That is the northeast trade winds and the southeast trade winds coming together, converging at the equator. And at the equator itself, these winds flow generally in a westward direction. Number two, you have a situation of low pressure. We already know that along the equator, you have relatively low pressure. And the reason why you have low pressure is because as a result of converging air, that is the northeast trades and the southeast trades, you have air that comes together from 30 degrees south and from 30 degrees north to the equator, as is shown by this small diagram at the bottom of the information for the equator. You have your trade winds coming together, and as they meet, they tend to rise up from the surface. And as air rises, it creates less pressure on the surface itself. You have to remember that you're dealing with a very warm area along the equator. This is in the middle of the tropical zone where you have a great deal of heat intensity. And so as a result, not only do you have air coming together and converging, but you also have very warm air, which is very buoyant. As a result, you have rising air. The third thing that you have as a result of this rising air at the equator, which in turn results from convergence, is calm winds, as I said earlier, moving in a westward direction. But more significantly, you have raining conditions in this area. And the reason why you have raining conditions in this area is because of again, converging air and rising air. As air rises, it has a tendency to cool off. We learned earlier that as we increase altitude, temperature decreases at a certain rate. And the same is true for a parcel of air as it rises from the surface. It has a tendency to decrease in temperature as it rises. And one thing that we're going to learn about later is that cooler air has less of a tendency to retain the moisture that's in it. And so what happens is that the moisture that's in it will be released at some altitude when the air gets cool enough to not to be able to retain the moisture that's in it. And that's when you get rain or some other type of precipitation. And so this is the third thing we need to remember about what happens at the equator. And then finally, you need to be familiar with the technical name given to this particular latitude. And that is intertropical convergence zone. The intertropical convergence zone. And the name itself implies convergence, as I've indicated already. It is also known as the doldrums, which you can see here. Actually, the equator goes by a number of names, but these are the two most common names that are given to the equator. The intertropical convergence zone, sometimes referred to as the ITC, and the doldrums. The second latitude that is important to understand as far as its weather situation is 30 degrees north, as well as 30 degrees south latitude. The first item that we need to remember about this particular latitude as far as the specific weather situation is the fact that it is a zone of divergence. A zone of divergence. It's just the opposite of convergence. In other words, instead of rising air, you have sinking air at this particular latitude. And as air sinks, it gets heavier and it exerts a greater amount of weight on the Earth's surface. And as a result, you have a situation of high pressure. And this is, in fact, a high pressure zone, a high pressure belt, a subtropical high pressure belt. Now, this is illustrated by the small diagram at the bottom. You see here 30 degrees north, 0 degrees over here, 60 degrees over here, looking at these latitudes in this perspective in a horizontal fashion. We see that as air diverges or sinks at this particular latitude, this causes a greater amount of pressure on the Earth's surface, and then it has a tendency to move away from this particular latitude. And so this is the nature of the vertical movement of air. We've already talked about the horizontal movement of air, wind, but this has to do with the vertical movement of air. And so the result is rather stable atmospheric conditions. Generally speaking, whenever the air does not move at all, or when it sinks or diverges, you have a situation of atmospheric stability, where you have very little chance of precipitation, very little chance of moisture being released into the atmosphere, because as opposed to atmospheric cooling, you have atmospheric heating as air sinks. And as the air becomes warmer, it has an ability to hold more moisture, and it's less likely to release the moisture that's already in it. And so as a result, the situation will tend to be extremely dry. In fact, at this particular latitude, you have extremely dry types of environments. For example, your desert environments are extremely dry, what we call arid environments. And the reason for this is because of the extreme high pressure caused by atmospheric divergence. The name of this particular latitude is the subtropical high pressure belt. And again, it gets its name from the nature of the pressure and air movement. And then finally, at 60 degrees north and south latitude, you have a very interesting situation, because at this particular latitude, we experience a great deal of the weather situation that goes on both during the wintertime and during the summertime. And so what you have here at this particular latitude, both north and south of the equator, is a situation of convergence, similar to the equator. It's a situation where air comes together, converges, and rises from the surface. And so as a result, it's another area of low pressure. Because again, as air rises, it exerts less weight on the surface. As a result, the pressure is less. And as a result of rising air, which will eventually cool, you're going to have a situation of instability or unstable air. And instability is related to moisture being released in the atmosphere in the form of some kind of precipitation. Usually rain, but sometimes sleet, snow, and hail. This particular area is referred to as the polar front. And again, it's very significant, especially in the northern hemisphere, because this is where we're located. At our particular location, that is the United States, we're pretty much in this general vicinity of the polar front. That is anywhere from 45 to 50 to 60 degrees north latitude. And so what happens at our particular latitude, where we're located, is that we have a great deal of storm activity because of instability. During the wintertime, we have snowstorms, especially in certain areas of the country. And as a matter of fact, right now there is a great deal of snow in the middle western part of the country because of the very cold air coming down from Alaska that we've been hearing about the last few days. But also during the summertime, obviously we have a great deal of storm activity. We're all familiar with hurricanes, not so much with tornadoes, but again, if you go further west to states such as Kansas and Oklahoma, there is a great deal of tornado activity. But even in the past few years, we've gotten more tornadoes than what we've been accustomed to. Of course, the situation in Raleigh a few weeks ago, where a tornado mysteriously, in the wee hours of the morning, touched down and destroyed totally a Kmart, as well as some fairly expensive houses in the northern area of Raleigh. Totally unexpected. Here in eastern North Carolina, about 6 or 7 years ago, there was a series of tornadoes that touched down in counties south of here that I believe 6 or 7 lives were lost. In Raleigh, no one was killed, but there was a great deal of damage done by these tornadoes. But this is another subject as far as tornadoes and hurricanes. Hurricanes we're very familiar with. A few years ago, of course, we had Hurricane Gloria, which was described as the most violent hurricane this century. And so we're pretty familiar with this stormy type of weather situation. But it all results, and this is the most important thing to remember, it all results not only from convergence, but because of what situation do you think that is different at 60 degrees north latitude especially, as opposed to the equator? At the equator, you have a situation of convergence. At 60 degrees north, you have a situation of convergence. But what is different at 60 degrees north that would cause storm conditions at this latitude, whereas at the equator, you have fairly calm conditions? Anyone? The temperature has a great deal to do with it. Specifically, there is a temperature difference in the air which comes together at 60 degrees north and 60 degrees south. If you look at this diagram, you have the polar easterlies converging with the westerlies at 60 degrees north. The polar easterlies is a very cold system of air, obviously, coming down from the North Pole. The westerlies, sometimes referred to as the prevailing southwesterlies, is a system where you have very warm air coming up from the south. And so whenever you have very cold air meeting very warm air, you have a situation that is likely to produce a great deal of turbulence or instability, which will eventually result in some type of storm situation, whether it be a snowstorm in the winter, a tornado, or a hurricane during the summertime. Of course, along the equator, on the other hand, you have a situation where you have two similar types of wind systems coming together, very warm wind systems coming together. So you don't have that much of a difference when air collides because it's the same in terms of temperature. So there's not that much turbulence, there's not that much instability. Although you have a great deal of rain because of convergence. As a matter of fact, along the equator, you have more rain than anywhere else in the world. Okay, are there any questions on either the nature of a diagram like this? Hopefully you're in the process of remembering the configuration of the diagram, but most importantly, you need to remember the significance of the diagram in terms of the specific weather situations within these strategic degrees of latitude. Okay, if you don't have any questions, the next time we will continue with a discussion of the result of atmospheric convergence and instability. We're going to talk a lot more about the releasing of moisture in the atmosphere and precipitation.